Hi everybody, let's get started today. Okay. No, sorry. All right, let's get started. Today we're going to be talking about planning under uncertainty. We'll talk a little bit more about what that means, and we'll talk about some techniques that have been used to address it and some of the limitations of those techniques. So the first thing we'll do is we'll introduce this kind of notation and the structure of something called sequential decision problems. We'll have a, I wonder how I lost this, but we'll see that, Gerks. Anyhow, what that should say is value iteration on there. But the Markov decision problems processes is one of the techniques for doing this. And to solve a Markov decision process, we have something called a value iteration. Just imagine it says value iteration there. And then another technique is policy iteration. And then we'll talk a little bit, and this is not a solution, of a different version of a Markov decision, which is a little bit more general, but also more difficult to solve, which is called a partially observable MDP. And then the second part, or some part of this class, is we're going to leave open for you to ask questions that you might have in advance of the midterm. So anything about material that we've covered, any questions that you have in line, you can just go ahead and ask here. This might be increased bandwidth versus Piazza. Okay? Okay, so let's get right into this. So in the planning techniques that we've looked at, not counting replanning and conformant planning and contingent planning to a certain extent, what's the thing that's sort of kind of irked you the most? It's saying, well, that's really nice, but. So what are some of those things? What is the thing that should affect you the most? If you're thinking that you're going to take these planning techniques, take them out to the real world, try to apply them to a real problem, what do you think those techniques have been missing so far? You know, the title slide should have given you a big clue there, okay? Right, so it's uncertainty, right? I mean, the world does not have this deterministic effect all the time. Now, how many times do you do something and it doesn't happen the way you thought it would do it? You're able to accommodate it, you're able to negotiate it, but how do you do it as a planner versus these techniques which were pretty brittle, even in the sense of a contingent planners? If you don't have those contingencies pre-programmed into those plans, you know, if it's option D and you only had A, B, and C, you know, what do you do? Right? So there's a big gap between these techniques and then actually being able to apply to a wide class of problems. There are a set of static problems which you can't apply these to because there's not high uncertainty in those. But yeah, as we all know, those are rare in the world. Okay? So the big thing is there's no uncertainty, right? No uncertainty considered. So it assumes the agent knows everything about the world and what can happen in it. And I don't know about you, but that's not the case for me. All right? So what are some of the sources of uncertainty that you might find in real-world problems? The agent may not know all the states of the world. That's a really hard one, right? And then you are caught into a situation where you get outcomes from actions that you don't even recognize. And then you have to decide, you know, you start trying to figure out if they look like something similar to what you do. This is really difficult. I'm going to stay away from this for the moment. Agents may not know what state of the world it is in. So I may know what states are possible in the world, but I don't know what state I'm in. I have some probability I'm probably in this state, but I could be in some other states, and I'm not sure. We'll talk a little bit about this at the end of the lecture, about how to address this. Here is one where the outcomes of actions may not be known. That when I take an action, the outcome is not deterministic. All right? This is the one we're going to focus on immediately now. All right? So the idea here is that I may not know exactly what action is going to happen, what outcome is going to happen when I take an action, but I do know within some probabilities of it's probably going to be this outcome, but it may be this outcome and this outcome with other probabilities. So that's the sort of model that we're taking right now. And we're going to talk about how to address that. So we're incrementally edging into uncertainty, trying to accommodate that uncertainty, and this is the dimension we're first approaching. Okay. So before we start anything, let's give what always I think is helpful, some motivating example, some simplifying example to explain things. All right? So the first thing is we're going to give this sequential decision problem example. And by sequential decision, basically I'm saying it's a set of steps, set of decisions that you're going to make in order to get from some initial state to some goal state. Right? And that's very familiar to what we've done in our planning techniques prior to this. So in this particular problem, it looks, it's just this kind of grid here. And you can start at this start state, and you can move to get into the goal states. And if you get to this goal state, you get a +1. And if you get to this goal state, you get a -1. All right? Pretty simple. So you begin at the start state. The problem terminates when either goal state is reached. The possible actions are up, down, left, and right, and assumes that the environment is fully observable. That is, the agent always knows where it is and what the states are. All right? And each cell here is considered a state. All right? When you move, you can't move into these obstacles. If you say you're going to take the action to say to move left here, and you can't do it, then you remain in the same state that you're in. All right? Okay, so if we always knew the outcomes of our actions, and we didn't have these probabilistic outcomes, then it would be pretty easy if we wanted to maximize our reward to figure out what the deterministic set of actions would be, which is simply to go up, up, right, right, and right. Right? Because we know that there's no uncertainty about it. If we take those actions, it'll get us there. But what if the actions are unreliable? That is, take this model for example. If this is your intended direction, you have an 80% chance that you're going to get actually to that direction. But there's a 10% that you might go to this at right angles of that intended direction. All right? So suppose you have that uncertainty now in the outcome of any action taken. All right? Then simply saying, up, up, right, 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 okay? The probability of reaching the goal state by executing that set of decisions, or those actions, is going to be 8 to the 0.8 to the 5th, right? Plus the small chance of the probability that you might go this way, right? So the path then is 0.32776. If you're a betting man, that's not where you want to be, right, to get there. Right, so you can see where you've got to start taking into account but note, this is still fairly structured. And the only reason I'm going to say this once is that you actually are able to know what these probabilities are. So it's still kind of fairly structured, and you know all the states. So it's kind of dipping your toe into the uncertainty world, but not really your whole foot. All right? There's a seat up here if you want to sit up here. You can't. No, okay, whatever you want to do. So the first thing I wanted to say is let's talk about what comes with these kind of problems. Well, one is there's this, as part of this specification, there's something called a transition model. And it's a specification of the outcome probabilities for each action and each possible state. Okay, so that's basically what we showed with the 0.8, the 0.1, and the 0.1, all right? So given a state and this transition model, given an action, it'll tell you what the probability of that action being actually assumed. So here's a notation here which says, given this state and taking this action, that you'll get into state prime, the next state, this will give you the probability that you'll actually get into that state by taking that action. All right? All along here in this particular model, we're going to assume this Markov assumption, which is that the probability of reaching the state S prime from S depends only on S and not on the history of earlier states. And so that's just the basic Markov assumption that we're going to assume here. All right. In order to try to figure out, where you want to go and what goal you want to do and what's the value of an action that you're going to take, you need to assign rewards and from those rewards gather the utility for a set of actions. So a utility function must be specified for the agent in order to be determined the value of an action, okay? Because the problem is sequential, the utility function depends on a sequence of states. That's also called the environment history, all right? And the rewards are assigned to states, i.e. R of S returns the reward of the state. So each state will be assigned a reward, and we'll talk a little bit later about what those values are you might assign, and we'll show some of the differences that occur if you give different values to states. From those rewards, we can run a function over to determine the utility of a particular action from a state going to another state. For the example that we showed, the motivating example, the reward for all the states except for the goal states being +1 and -1 for those rewards, is going to be negative 0.04. Now, if that seems slightly high magnitude there or a high resolution, we'll show you what the differences are if you just slightly give different values there. The utility function is the sum of all the states visited, i.e. if the agent reaches 4.3 in 10 steps, then the total utility is 1 plus 10, 1 being the utility of the state, the 4.3 state, plus 10 times 0.04, which is all those intervening states that you took to get there. So the utility would be 0.6. All right? And then the negative reward, notice that this is negative, is going to incline the search to stop interacting as quickly as possible. Because the more intervening states you have, the more negative reward you have, and then your utility decreases. Okay. So let's talk a little bit more about what an MDP is. It's going to be a specification for a sequential decision problem for a fully observable environment. Like I said, you know all the states and you know the outcomes and the probabilities for each action, with a Markovian transition model and an additive rewards. These are the components of that specification. You're going to start off with an initial state, whatever state you're in, the transition model, the probabilities given the state and the action of getting to that next state, and the reward function for each of the states. Okay. What is a solution for an MDP? Well, since outcomes of actions are not deterministic, a fixed set of actions cannot be a solution, right? Because you don't know that you're going to be able to get to where you go, where you intend to go. So in this case, you need to be able to have wherever you end up going, you still need to be able to take optimal decisions from that point. So even if you don't go where you expected to go and you go to a lower probability space, you still need to be able to start that lower probability space, that state that you're in, and still take optimal decisions from that point. So you need a set of actions that can get you to a solution given the uncertainty of the outcomes of the actions that you will take. A solution must specify what an agent should do for any state that the agent might reach. A policy denoted by pi recommends an action for a given state, i.e. pi of s is the action recommended by policy pi for state s. So given a policy pi, it's going to say whatever state you're in, it'll give you the action that it prescribes. Okay? And then we'll talk a little bit more what it means to have an optimal policy. Okay. So how do you kind of rank policies? What do you say is a good policy, right? So since the environment is stochastic, at each time given a policy is executed, starting from the initial state, there can be different environment histories, right? Every time if I have the same policy, I have the same problem, I start in the same initial state, and I have the same goal, every time I execute it may be different due to the stochastic nature of the actions and the outcomes. Therefore, the quality of a policy is determined by the expected utility of the possible environment histories generated by that policy. So you have to look at all the different possible states in order to get the value and sum them up for the value of that policy. Okay. So what's an optimal policy? An optimal policy is a policy that yields the highest expected utility. So given each decision you make, or every state that you go to, you would expect that the expected value, meaning the action that's prescribed from that state with the highest utility, will give you the highest expected value, and that will be the highest, that will be the optimal policy. So basically what you're trying to do is maximize the expected utility for that policy. So the optimal policy is denoted by pi star. Once a pi star is computed for a problem, then the agent, once identifying the state, whatever state it's in, right? If I intended to move this way, but with a low probability I move that way, even if I go to that state, it'll still recommend the optimal action to take from that particular state, wherever I am at. And each step, you're still going to always be recommending that optimal state that will maximize my utility from that state. Okay. So going back to our example, here's the optimal policy given the rewards associated with each one of the cells. And we're doing additive. We're adding up those things to figure out the maximum utility. And if you notice, here it's like this is what you would expect, shortest route to go here. Here seems a little strange. Why isn't that we're not going up this direction, right? Why don't we go up this direction? Well, the choice of the reward is basically kind of disinclining us to go near where we might potentially go into the bad terminal state, the bad goal state, which is this one. Because remember, if we're here, right, there's still, and we intend to go this way, there's still 0.1 chance I can go this way and end up with a bad value here. So by having a negative value there, it's kind of disinclining us from wanting to go there. All right, so that's already kind of, guys, your ears should be sort of perking up here and thinking, oh, wow, it's really sensitive to that. Really sensitive to that value. All right. So what are we doing here? We're trying to balance, risk and reward here. So the balance of the risk and reward depends on the value of R of S, right, for each state. Characteristics. This is, wanting to balance risk and reward is something you do all the time, right? You think, well, I can blow off that homework assignment. We'll see what that gets me, right? Hopefully you don't ever do that. But we make these kind of accommodations. I'll spend 20 hours on this. I'll spend 5 hours on this. We do different kinds of accommodations. So this is something we do all the time. It shows up a lot in many fields, as we can imagine, AI, but also operation research, economics, control theory, etc. So you see these models studied not just in AI, but in all these different disciplines. Let me show you, the next few slides I'm going to show you is a notion of a pi star for different R values and show you how those policies have different behaviors. Okay, so here we have, this is all not counting these goal states. R is less than negative 1.6284, all right? In this policy, what does it look like it's doing, right? It looks like it's trying to get out of the environment as fast as possible. It just doesn't care, right? It just wants to get out. Because remember, every step it takes, right, it's still it's getting a fairly high negative value here. So it just wants to get out. It just doesn't care. It'll go out and the other way. Yes?
Can you explain again what R means again?
So R is the reward that's associated with each one of the states. So R is the reward. That's just given.
That each over R is minus 0.04.
Right.
Okay.
Right, exactly. So here's an R between these two numbers, okay? And here it's like, take the fastest route to the positive value here, but don't concern yourself with risk here. So you're more kind of risk, you're not risk averse, basically. Here is, you just don't want to take any risks at all. All right, you just don't want to take any risks. You want to be safe. You want to get out. If you're anywhere, you're trying to always come back in. And here, since every step you take gives you a reward, you never want to leave. It's like, you know, you're in like in Shangri-La or something. You're really happy here. All right. So you always want to stay in here, and you always want to keep moving around here, because the more you move, the more, and you don't get in certain states, the more utility you get. Yeah.
The obstacle doesn't have any cost associated with it?
No. Yeah, no. So what happens is that if you try to move there, it just comes back.
Okay.
It's a no op.
Okay.
Same thing as if you're going this way.
Okay.
Right. So as you can imagine, so all this is doing is trying to avoid these states.
Okay.
Yeah. Yes.
Like, how do you, like, -1 except 10, and is it a kind of, like, a bad reward, or, like, what, how do you include?
This one right here, you mean? Yeah. So this is a bad reward. I'm sorry. All these other states would have these rewards, but these are the rewards for these states. Okay. Sorry. So you can see that it's pretty sensitive to the reward that you assign to the states. Right? So you can also imagine now you should be thinking in your heads, if I was doing a real world problem where I was planning something, how would I choose those rewards? And what is the risk and utility I'm trying to balance here? And how would I do that by choosing these values? All right. Another issue that shows up when you're making this kind of planning is what kind of environment are you in when you're doing this planning? And what I mean by that is whether there's sort of this ultimate deadline where everything just stops. Or is it infinite? Is the horizon infinite, right? So in a finite horizon, there's a fixed time n after which nothing matters, right? It doesn't matter. If you get to the goal state, for example, in our previous problem, after time n, you don't get the reward. Time's up. You lost. All right? So the key here is that the optimal actions can change over time. So if n equals 3 in that previous state, then the option action, if you're starting at 3,1, is to take that shortcut. Because if you won't get it because the other one takes you too many steps to get there. But if the n is 100, then you might not take that path. Right? So it is contingent. This means that basically it's a harder problem because it changes depending on what those deadlines are and where you are. The flip side, which is I should say the more straightforward, easier problem, is the infinite horizon. This is the one we'll be focusing on right now, and that there's no fixed time, and the optimal action depends on the current state. And the optimal, when there is a finite horizon, the optimal policy is considered non-stationary. That's because it changes depending on the time. And here, when it doesn't change, it's stationary, and that's because there is no deadline out there. Now, I don't know about you, but almost everything I do falls in this category. Right? Yes?
Like, non-stationary optimal policy, does it mean, is it like some kind of reinforcement there?
Well, I mean, there's approaches to that, but I'm not going to address that quite yet. But what this means is simply that there is this, there's this deadline out there, and that you don't have to solve the problem contextual to that deadline. You know what I'm saying? So it doesn't have to switch back and forth, depending on where you are in that state. It's not one more factor you have to keep accounting. The other thing is this sort of assumption that you have stationary preferences, that your preferences aren't going to change as you're planning, right? You're not going to say, oh, this is what I want now, but tomorrow I might want something different, or tomorrow this is what I want tomorrow, but now I want something different. My objectives, my value scheme, everything I want to do is still the same. It remains the same, independent of those time. All right, so the assumption about preferences has remained the same independent of time. If you prefer one future to another starting tomorrow, then you should prefer that the future, you should still prefer that future if it were to start today. So it doesn't change. Given stationary preferences, there are two ways to assign utilities to sequences. This assumption is pretty powerful, and so it holds these tight ways about how to accumulate utilities and retain this property. So these are going to be the two ways for assignment of utility to state sequences. First of all, I would say that utility functions for environment histories, sequences of action is dependent on, is denoted as this kind of utility of the history of SO, S1. These are just a set of states, just a notation. Okay. And there are two methods. One is the additive rewards, which is the method that we saw in the example, which we simply added up the rewards of the states. The other one is discounted rewards. And it's the sum of this kind of progressively discounted rewards of state. You basically, the history of that environment, and the utility of the history of that environment is the reward of the state that you're in, plus a discount, which is represented here by, I guess, and that's gamma, I believe. So gamma of R of S of 1, which is, this is just some value, and this value has to be between 0 and 1. All right? And with each step you take, this would be steps you're taking, it's raised to that step number. Okay? So if you saw that gamma was 1, then this would be exactly equivalent to the additive. Right? If you see at the smaller this gets, then the smaller these get as you go out into the future. And so future rewards, future steps, count less. And as it gets closer to 0, the less you care about the future. You're more concerned about the near horizon. Okay? Okay. So one little oddity that comes out, but it's not an oddity, it's a little troublesome, is that if all environments have an infinite horizon, and that means the terminal states aren't reached, then using additive rewards results in comparing infinities, basically. So the idea is that if you keep going, forever on these things, you don't reach terminal states, then how do you know one's better than the other? Because they'll all be infinity. Maybe some grow faster than others, but you don't want to be in the business of comparing infinities. Right, so there are three possible solutions. One is to use this discounted rewards, which is essentially that if you have a R max, which is sort of the maximum utility that you can gain for any state, you can compute sort of from this infinite geometric series that this bound will bound the utility that you can gain. So you're guaranteed not to be into the infinity range. The other one is to have this ensure what's called a proper policy. And a proper policy is a policy that is guaranteed to reach a terminal state. So you basically say, oh, I'm not going to be in this state. So you have some kind of insurance of this. But that's complicated to ensure. The other one is to compare in terms of average reward, the average reward gained. But there are a number of difficulties with this, and it's difficult to analyze. So the most popular one to use is this discounted rewards. Okay. So there are a lot of policies that you can assign to anything, and you want to try to figure out which policy is the one that you want to use. As we said before, the optimal policy we've defined as being maximizing the expected utility. But just a step back from that, all we're saying here is basically we want to find the policy here where the expected utility, given the discount factor for each step and the reward for each step, given that policy, is the greatest. And that's just how we're going to choose which policy is the maximum policy. And basically that comes down to is choosing the one that has the maximum utility. Okay. So how do we do this? We know what the problem is. We know what the problem looks like. We know the problem structure. But how do we assign those utilities? Right? In particular, given that the utilities depend on the utilities of other states. So one popular method is something called value iteration. And it's an algorithm for computing the optimal policy. The basic idea here is to calculate the utility of each state and then use the state utilities to select an optimal action in each state. It's kind of recursive, and so now we have this problem of having to sort of simultaneously get the utilities for all the states. So a little bit more notation here. The utility of the state is the expected utility of the state sequences that might follow it, which are determined by a policy. So given a state, what are the possible states that might follow it? You are going to add them up, and that's going to help you determine what the utility of the current state is. Let u of pi of s be the utility of a state, and st be the state the agent is in after executing pi for t steps. Then the utility given policy pi of s is again going to be this kind of expected value where you add up all the rewards of the future states, and that'll be plus the reward of itself to give you the utility of that state. Okay. So imagine that value iteration has run on all these things. Now we've got these utilities. I'm just showing you this ahead, and then we'll go back a little bit about how we compute them. So for example, given the initial one, we're negative 0.004 for the reward function for the other states, we've run them all through, and these are the utilities that were discovered by value iteration. All right. Note that the utilities closer to 4.3 up here are going to be higher because they have fewer steps to go to. So if you imagine that the initial state was actually up here, then you're really high utility because you didn't have to go through these intervening steps that have the negative reward. All right. So central to doing value iteration, just to solve to compute the utilities, is something called the Bellman equation. And the Bellman equation essentially is it's going to be this equation, but essentially it's a way of computing the utility of a state. All right. So let me start up here. The optimal policy pi selects the action that maximizes the expected utility of the subsequent state. All right. So here it's saying here for the optimal policy of S is you pick the action that gives you the greatest utility of all the possible states that come up plus their utilities. All right, and that gives you the back. And you're going to pick that. So what you do in order to get the utility of a state is essentially you define u of s as the utility of s plus the discounted utility of the next state, assuming the optimal action, i.e. So the utility of s is going to be reward of the current state s plus the discount here, plus you're picking the action that's going to have result in the highest value given the probability of going from S to S prime given that action and the utility of the subsequent state. So you add all those things up, give you the max one, pick your action, get the highest value here, add the reward to that, and that'll give you the utility of S. So what you're noticing, you should be noticing here, is that you're having to get the utility of subsequent states. Right down here, right? So you have this kind of, simultaneous problem. You need to be able to get this plus the values of those. All right. So let me just give you a kind of example for one of the cells in our example problem. All right. So for one of the cells, for the equation of 1, 1, given the setup that we have, 0.04 is the reward of that state, right? And then you're going to look at this is the discount value, and now we're doing our argmax that we saw in the previous slide here of all the possible actions that could be taken, right? And of course, because of that table I showed you earlier, right? We can look up the values because of this table, but that's not the way value iteration is going to work because you don't know what those values are yet. But if you knew what those values are, you'd simply look these things up in the table, add up all these things, pick the one that had the maximum value, and sure enough, when we plug in the members from slide 26, we find that up is the best action. That is, this has the highest value. So that would be the one we would choose. All right, we're still in the problem of how do we actually figure out these utilities, the states. All right? So we're going to use these Bellman equations to solve the MDPs. If you think about it, if there are n possible states, then there are n Bellman equations for one for each state. All right. To compute the n utilities, we would like to solve simultaneously the n Bellman equations. All right. So one of the things that's a little difficult about this is that because it's a max, it's not linear. All right. So one of the approaches for handling this, rather than just sort of a kind of a linear algebra approach on these things, is to use iteration, and that's where we got the name from value iteration. All right. So using the iteration, we're going to apply the Bellman update, which is essentially the same thing as the Bellman equation, but you're going to get for each utility of the next iteration is going to be so I plus 1, where I is the iteration for the next iteration of this S, is going to be reward of the S for the state, plus again what the value is for the maximum state given the to get to this state, given the current state. So basically what you're going to do is you're going to start off with a bunch of values for the utilities. They're not right. And then you're going to keep iterating over them and change them as you start reflecting on each one until the change basically becomes very small. So you're converging. And we'll talk a little bit more about that. So the value iteration algorithm here is it takes an MDP with states S and a transition model T and a reward function R and a discount gamma. And it takes an epsilon, which is the maximum error allowed in the utility of any state. So that's going to be basically when we're close enough, right? And what we start off with is a vector of a set of basically two vectors, but that's only just because they're being copied back and forth. But U is going to be a vector of utilities for states in S. Initially, all the utilities are 0 for all the states. So for every state, every utility is just 0. Just starts off that way. All right, and this is just an initialization variable for the delta to see how much you've changed through an iteration of them. So then for each of the states in S, you're going to calculate a new utility for that state, okay, given the vector that you have. And you're going to look at it, and you're going to look at all the probability of all the other states, and plus the reward, and get the new value for that S. So that's one iteration through. And then you have to do that for each one of the states. If that difference is greater than delta, then you set delta to that difference. And you go through all the states to do that. And if the delta is less than this, basically this small error amount, this represents the error, where epsilon is the error, then you return the U. This is essentially, the book describes in more detail what this is, but essentially you think of this as close enough. Close enough. There are some issues about this, and we'll talk about it in a second. But the point here is that I hope everybody gets the point here, that you're going to keep iterating through these things, changing the state values, and making sure that none of the changes in each one of these, once you go through the loop, is not greater than that epsilon. If it is greater than this close enough, then do it again, and it'll keep converging. And there is a discussion about why this converges in the book, but I'll leave that to the book, not in the lecture. All right, it has to do with this contraction principle. All right. One of the issues about things is think what it would mean if they terminated too early. If they terminate too early, too big an error, right? Then it may be that you're going to lose the appropriate action. Because remember, ultimately what you're doing is getting a policy which is going to tell you whatever state you're in, what's the right action to take to get there. And if you terminate too early, it may be that you don't get the right action for those states. So this is typically very small, right? But we'll talk a little bit more about this in a little bit. All right. Hopefully that's clear to everybody what that is. Yeah?
If you terminate lately, does it compromise on optimality or completeness?
Well, it's going to compromise on optimality for sure. There probably are states. It's always, have to think about that. Good question. But I was referring to optimality here. Okay. So here's giving you some sense of things when they converge. as we're going through and we're iterating through those things, how these values converge. And these are some selected states, the 4, 3, 3, 3, 1, 1, 3, 1, 4, 1, just some selected states. And these are the number of iterations that we've gone through in our value iteration. So note that it's kind of interesting because as you see this, some of them go down before they go up, right? It's kind of a funny thing. Why the values go down, and then they start to get higher and higher, and then they level off, which is what we want to see, right? And the reason they go down is because they're far away from the goal state. And initially in those first few passes, that kind of reward from the goal state hasn't propagated back to those states yet. So they don't get the benefit of the reward until you get through enough of them that the intervening states have been propagated, the values have been propagated to them, and now they're propagated to these very early states. All right. This other one is the number of iterations required to guarantee an error of at most EC. Basically, the takeaway point of this is that to get very small errors, it takes a lot of iterations. All right. It takes a number of iterations to get to them. So keep that in mind again. And this is on a really small world problem. So that error, there's a correspondence between that error and your need to get the true utility values for each of those states. Maybe approximate utility values are good enough. But the question is, how approximate is good enough and when is it bad? Right? So what matters is that the utilities are good enough to recommend the optimal action in each state. So you may not have to have the exact utilities as long as they have the right ratio to each other. Right? In practice, pi of I often becomes optimal before u of I has converged. Often, what utilities you have are good enough, long before you're beneath that error. Okay. For our example, the policy is pi of I is optimal when I equals 4, right? Even though the maximum error in u of I is still 0.46, quite big. So, but it's like after you solved it. I mean, it's a difficult problem. So what that got people thinking about is, okay, maybe we shouldn't be looking in this value space. Maybe we should be looking at this utility space. Maybe we should be looking in the policy space and try to search the policies. Policies are defined by the actions you can take. Maybe those are fewer to search by. So we can search the policy space. The basic idea is that the policy evaluation is to start with a random policy, pi of 0, and calculate the utilities based on that policy if that policy were executed. So notice that we've already got something a little bit easier here in terms of that because the policy is going to say exactly what each state is going to do. All right, so we've taken away that max number in those Bellman equations for each of the states. So then policy improvement is to calculate a new maximum expected utility policy, pi plus I plus 1, next iteration, based on computed utilities. So again, go ahead and propagate based on those utilities, and then iterate until the policy does not change. So here's the example here. The MDP with states S, transition model T, again takes those two vectors of utilities for states in S. Initially they're 0. The pi, a policy vector indexed by a state initially random. So we just start off with this kind of random policy that just kind of picks actions for each of the states. Okay. We do this at the policy evaluation, and I'll talk a little bit more what the policy evaluation means here. But essentially, that's going to give me the utilities. I set this state variable just to be true, just to see if things have not changed. Because when it's nothing has changed, I'm going to go ahead and return that policy. All right. And then for each state in S, for each of the states in S, I'm going to again look to see if if I take looking for the max arg such that that the action is going to create a bigger value than it was on the previous one, then I'm going to replace that in the policy. All right? And that's what I'm doing here. I'm going to create the one with the bigger, with that action. And so I've changed the policy. I keep doing this, changing those things, until nothing changes. So I've converged again, okay? If I've changed them all and nothing has changed, then I go ahead and return that policy. That should be up high, by the way. Yeah?
In value iteration, what does the factor of 1 minus gamma upon gamma represent?
Let me see where you're talking about.
Value iteration.
Oh, in value iteration. Okay, in the previous one. Okay. What does, say it again?
We were checking that when delta is less than epsilon into 1 minus gamma upon gamma.
Oh, you mean the close enough one?
Yeah.
Yeah. So there's a value there that basically is, like I said, it's the close enough value. The reason it's done that way is there's a sort of something called an interest rate, which is the reverse of the discount factor. And I don't have it exactly right. I don't want to misstate it right now for that. But that's essentially what that's representing. Okay. Here we don't have the most equivalent we have is change, but that doesn't really represent that. Here we just keep doing it until we get no more changes in the policy.
And in value iteration, the policy is to go to the state which has the highest utility.
In value iteration, what you're doing is calculating all the utilities, right? And what you're ultimately doing is going to pick a policy that is going to have the highest total cumulative expected utility, maximum utility. So you add them all those up. So you are moving to each one of those states to the highest utilities. Okay. So for now to evaluate, to do this, remember I talked about I was going to say about policy evaluation here. Because policies are fixed, the max operator is removed and the standard linear algebra methods can be applied to solve the simultaneous equations where you have multiple states and trying to save all those utilities. The complexity for doing that is O to the n of 3 n cubed. For large state spaces, this might not, that's maybe just too big to address. In general, we'll talk a little bit more about what MDPs in large state spaces. But one of the accommodations for that is to use this kind of modified policy iteration, which you can do some number of value iterations, and it's a simpler value iteration than you saw in the other one, in that you're already given the policy, so you already know rather than having to run all the equations. Remember, for each one of the actions, you only have to run the one that's prescribed in that policy. Right? The number of value iterators is simplified because the policy is fixed to get a reasonable approximate of the utilities. So there's a question about how much, when is approximate, when is it good enough? But this is a studied way of doing this modified way, which means that you might not have to do this, but when you have a large number of states, you might still do a number of value iterations just to get the utilities and then substitute back into the policy if they're greater. As part of the policy search. Okay. So before sort of talking about the use of MDPs, I want to mention that there are sort of a number of different other types of variants of MDPs. One of them has to do with partial observability, and it's going to be called POM MDP. I'll talk just a little bit about this. There's also another ones, lots of additional ones, even variants within the POM MDPs. There's one called DEC MDPs, which is a distributed version of this. Usually you see this in multi-agent for optimization and planning. All these are basically addressing more uncertainty. So they kind of are more difficult to solve. There's more uncertainty. So in this case, remember before we say, oh, okay, the outcomes of actions are not deterministic. So that's what we addressed when we went to MDPs. Now we're going to address even an additional piece here. Is what do you do if, another source of uncertainty, what do you do if the system state cannot always be determined? That is, you don't know what state you're in for sure. You don't have 100% reliability that I'm in like, square 0, 0. I don't know for sure. So action outcomes are not fully observable. So then you use what's called a partially observable MDP or a POM MDP, and you have to add something more to the model now because you're trying to account for this uncertainty. So one of them is a set of observations, O, to the model, things that you've observed. An observation distribution, so given utility, to get a utility of the state, it also takes the observation that you've seen for each state, and an initial state distribution. So that would be like, what's the probability of me being in this state, right? In this state. So, like the initial ones, you might see 1/9, 1/9, 1/9, 1/9, 1/9, 1/9, and the goal state and the two ones are probably 0, 0. Okay? That would be like the initial vector. So just to go on a little bit more detail about POM MDPs, once you have one, sort of the general idea here is that given the current belief state B, and belief state meaning the state that the probabilities that I'm in this state, the probability I'm in that state, probability I'm in that state, that distribution, execute the action A star prime given that B, belief state. You take that action, you receive the observation again, and then you're going to update B, that distribution based on what new observations have been made. So that's sort of the way that you would use the MDP once you've solved it. Solving, I'm not going to go into how you solve an MDP, solving the POM MDP, but essentially you're going to solve it as something that's called as a continuous MDP. You convert it to this continuous MDP. It's going to require calculating a probability distribution over the possible states given the previous observations. Okay? Again, this is harder to solve than even the MDP is. Okay? So what are the big problems with MDPs, POM MDPs, the variance, DEC MDPs? Especially, I can talk about DEC MDPs for a little bit even. They don't really scale. You can see that they're kind of a function of all the states that you have. And in real world, this toy problem had very few states. There have been lots of different methods to try to accommodate this, to abstract out, to pick out the features of the significant states that matter. And those all have worked. I mean, those have all worked to a certain degree. But at least in most of the real world problems that I work in, MDPs have not been very applicable. And I'll give you an example. As you know, I think I mentioned this before, is that I worked in something that was called, that had a natural disaster response. And there, in this program I was in, there were competing teams, which is one of the favorite things that DARPA likes to do. And one of the teams was an MDP-based solver for this problem. And the way the program was structured, initially we just did synthetic problems in the beginning. And there was a language for that sort of this, as we saw, HTN type structure of a language. And it was augmented with ways of accumulating quality. I don't have to go into details, but understand that certain actions could get you more quality than other actions. And that was the way the initial problem was done. They built a solver, the MDP people built a solver for this. And in small problems, they could do well. In fact, one of the evaluations for DARPA was to compare against quote-unquote optimal, which was in itself a global MDP. But it could only work on very, very, very small problems until it rapidly got beyond the scope of being able to scale. This is before any of the activities were located, where we had to consider locations and where you were. So all these things were non-located things. One of the killers, and you can imagine this being a killer, is that any action could be aborted any time. So at any time you run it, you can run it for 2 minutes, 1 minute, 5 minutes, 10 minutes, and you could abort it. You wouldn't get quality for it, but you might abort it in order to use that resource on something else that would get you more quality. Knowing that you could abort it at any time destroyed the states, number of states here. It blew it up, basically. It couldn't work very well on the bigger states. When you threw in the fact then that tasks had to be done at particular locations, and that there were setup dependencies, the time you took to travel to get to those different tasks, that also blew up the state space. All right, huge blow up the state space. So one of the things that that team did, and there have been other approaches this way, is there have been attempts to use sort of this hybrid where you do an MDPs up to a certain horizon, basically. And then for anything that's above that, where you're looking for the utilities of states that are above that, you use estimates. Sort of this heuristic estimates based on some kind of heuristic search that you go for sort of out to the advance. I should say that this problem that we were working on was not an infinite horizon, but it was a finite horizon, both finite in the deadlines of particular tasks and finite on the overall scenario. The hybrid worked to a certain extent, but rapidly they found that those estimates they got actually weren't good enough. They ultimately had to basically kludge together a situation where they would say if the problem was this big, they make an estimate how big the problem space was. If it was this big, they'd use their hybrid approach, and if it was bigger than that, then they used a completely local greedy search approach, just because it wasn't something that would expand. There have been work done on like satellites, positioning, defense scales, where MDPs have worked actually fairly well. These are, as I said, if you can identify the states and they're not particularly volatile and the state space is not particularly gigantic, then you can actually get away with some of this. As I said, most of the problems that I've worked on where I'm in this dynamic situation, I should add that one more case, is that often problems like natural disaster response, you don't have all the information up front. So you can't solve an MDP up front. Because what happens is that you go out and you discover information. So in this case, you discover, oh, how many casualties at a site? What what utilities need to be fixed? Power, water, electric. And at that point, you then have to make plans in real time, dynamically. So you can't solve these in real time. So that also limits the ability to use this because as they expand very big, you don't have the time to solve them in the real time of which you have to respond. So these are all some of the limitations. They have been used well in some context. I think they still suffer from that, but that's a personal opinion, that they still suffer from the calculation piece. So that's it for the probabilities, probabilistic planning for this piece. I think now I'm going to shift over to the opportunity for you guys to ask questions. If you have questions, now, I'm looking at your faces and you're all looking dead there, so that's not a good sign. But if you have any questions about the midterm and about things that we've studied up to this point, anything? Anything? I feel like that science teacher, Bueller? Yes? So I think there's a partial answer here. One will be, I think, will be everything that will be in the lectures. And the question is whether it's this lecture.
Yeah.
Yeah.
Fair game.
Fair game. Yeah. So I think everything in the lecture is going to be covered.
It's make sure. I think the mic can pick you up. Yeah. Everything in the lecture so far. It is closed book, so we're going to design it to be answerable with closed book, meaning that we're not going to ask you to write code out by hand. We're not going to ask you to derive any math that's too complex. There's going to be a little bit of math on here. We do like math, but it's not going to be too complex. But yeah, everything up to now is fair game. Tomorrow, because actually we sort of weren't sure how much we would get through, tomorrow we'll just post a list of all the topics that there is. But really, it's just the slides that are up, and I think the slide I'll put up today, and so it'll look at the slides. There is the additional reading material there as well that we highlighted some of these, but that's kind of been sporadic because really the notes have been the main resource, and the slides have been the main resource. So look at the slides, look at the list that we post. The format is going to be short answer, and short answer meaning either a short derivation or a short sentence description, and then multiple choice. That's all there's going to be. So that's it.
Right, and as he said, I think it will be designed to be doable within an hour.
Yeah, the goal is to make it doable within an hour, and you have an hour and 20 minutes.
Right, so that should give you a chance to not sweat it as much.
And I mean, at the same time, it is an exam, so if everyone got 100, it wouldn't be a very good exam. So I guess, sorry. So there will be some questions that you might get wrong, but one thing that we actually maybe did simplify, I think is in syllabus, is that, or maybe it's not, is everything's graded on a curve here. So we will look at what scores people get in grading the actual exam here. So don't stress out too much. If we wildly miss the guess here, which is possible, given this is the first time we've taught this course,
right?
That we have, it will be adjusted. So the goal is to have some sort of way of showing what you've learned so far, and we're not out to get you, to trick you out. That's what the homework is for. So I mean, class polls for that. We're here just to show us what you've learned so far. That sort of answered most of the general questions about
the structure of the test. Yeah. You don't have any specific questions about any of the material? Oh, there we go.
Any sample exam?
No, there's no sample exam because we haven't written an exam before. So it's going to be, again, we'll put out a little bit of a sheet tomorrow about kind of the type of questions and the material, but there's no past exams to base this on, so we're not going to write 2 exams and have one be a fake.
That's right. That's a complete outlier, but okay. Any other questions about any of the information? You all feel confident? Okay, well, this is kind of early.
All right. Well,
Okay.
sounds
All right, I was leaving 20 minutes out for it, but if you don't have any questions, you don't have any questions. All right, thanks.